Okay, let's dive in. We're about to decode a secret language. It's the language that powers our entire world, from the phone in your hand to the satellites up in orbit. It's the language of electricity, and honestly, once you understand it, you'll see everything a little differently.
You know, this quote really gets to the heart of why this matters. Think about NASA's Mars rover. It's one of the most incredible machines we've ever built, just packed with circuits that have to work perfectly every single day, millions and millions of miles away from help. There are no technicians on Mars.
So, take a look at this. This is a real-world circuit diagram for a radio. At first glance, it looks incredibly complicated, right? A total mess of lines and symbols. But here's the secret. All of this, the whole shebang, is built on just a few surprisingly simple rules. And today, we're going to learn them.
So to understand this language, we've got to start with the most basic word, the absolute foundation of all things electrical, and that word is charge.
So what even is it? Well, charge is just this fundamental electrical property that the tiny little particles making up all matter have. You know, like electrons, which have a negative charge, and protons, which have a positive one. This property, which we measure in something called coulombs, is really the hero of our story today.
And to give you an idea of the scale we're talking about, a single coulomb is the charge of about 6.24 times quintillion electrons. I mean, that's just a gigantic, mind-boggling number. It's why in the real world, you'll almost always see us talking about tiny, tiny fractions of a coulomb, like microcoulombs or nanocoulombs.
And charge plays by one very important, completely unbreakable rule, the law of conservation of charge. You can't make it, you can't destroy it, all you can do is move it around. And that sets up our next big question. What happens when charge actually moves?
Okay, so we've got charge. Now let's get it moving. This brings us to our next key concept, current, the electric flow.
So when charge starts moving, we call that an electric current. But it's not just about the fact that it's moving, it's about the rate of that movement. How much is flowing? Think of it like a river. It's not just that water is moving, it's how much water flows past a certain point every second. That rate of flow is what we measure in amperes, or just amps.
Now here's a funny little historical quirk for you. Way back in the day, Benjamin Franklin took a guess and said he thought electricity was a flow of positive charges. Well, it turns out he got it backwards. In most wires, it's actually the negative electrons that are on the move. But his idea stuck. So by convention, we still define the direction of current as the direction a positive charge would flow.
And this flow basically comes in two main flavors. You've got direct current, or DC, which is a nice steady flow in one direction. Think of a battery. And then you've got alternating current, or AC, where the flow actually wiggles back and forth. That's the stuff that comes out of the outlets in your house.
And this little table illustrates a super important point. Direction really, really matters. A 5-amp current flowing to the right is the exact same thing as a negative 5-amp current flowing to the left. It's the same amount of flow, just in the opposite direction.
Okay, so we've got charge. We know that when it moves, we get current. But this leads to a pretty obvious question, right? What's making the charge move in the first place? It doesn't just go on its own.
The answer? Voltage. If you think of current as the flow of water in a pipe, then voltage is the water pressure. It's the electric push. It's the force that gets everything going.
To be a little more specific, voltage is really about energy. It's the amount of oomph required to move a unit of charge from one point to another. And we measure it in volts, named after Alessandro Volta, the genius who invented the very first battery.
Now this is a crucial distinction. It's something that trips people up all the time. Current flows through an element, like water flowing through a pipe. Voltage, on the other hand, is something you measure across an element, like the pressure difference between the two ends of that pipe.
So let's recap the story so far. It's actually a pretty simple cause and effect chain. You start with the particle, charge. Then you apply a push, and that's voltage. And the result of that push is the flow, which we call current. See? Particle, push, flow.
Okay, so we have a push causing a flow. Now, whenever that happens in the real world, work gets done. You know, a flowing river can turn a water wheel. In electricity, we call this concept power. It's the result of that push and that flow working together.
Power is simply the rate at which energy is being used or absorbed, and it's measured in watts, which is a term you already know. It's exactly why a 100-watt light bulb is brighter than a 60-watt one. It's just converting energy into light and heat at a much faster rate.
And what's so beautiful about all this is how elegantly it all fits together. The formula for power? It's just voltage times current. That's it. The power you get is literally the strength of the push multiplied by the rate of the flow. Simple, elegant, and incredibly, well, powerful.
But there's one last little piece to the puzzle. The direction the current is flowing tells us something really important. If the current flows into the positive end of an element, the power is positive. That means the element is absorbing power. Think of a light bulb or your phone when it's charging. But if the current flows out of the positive end, the power is negative, which means the element is supplying power, like a battery or a power plant.
Okay, so that's the theory. Charge, current, voltage, power. Now that's connected all back to something we all know and probably pay for. Let's take this from theory straight to your TV.
See, this isn't just abstract physics. This is literally how your electricity bill gets calculated. The utility company is measuring the energy you consume, which is simply the power your devices use multiplied by how long you use them. It all comes right back to these basic ideas.
So the big takeaway here is this simple four-step story. It all starts with charge, the particle. Voltage is the push that gets it going. That push creates a flow called current, and the result of that push and that flow working together is power.
Every single electronic device in your life speaks this language of push and flow. Your toaster, your laptop, your car, all of it. So now that you understand the basic words, the basic grammar of electricity, what do you see differently?